We have talked about the Fermat's theorem, the extreme value theorem, and the extremum and the extrema and minima. We talked about those values, and I gave you a certain definitions that when we are talking about the absolute maximum, absolute maximum or the global maximum is actually the largest value the function can actually have, and when we are talking about the absolute minimum, it is the slowest or the smallest value a function can actually have. And then we started to talk about local maximum. Local maximum, you can say that it is a point in the function such that all the neighborhood, if let's say we're talking about a local maximum, all the neighborhood are always less than that point, or the point close to it are smaller than it, something of this type. So we're having some sort of a turning point at that point. So at this point, all the values that are close to it, they are less than that, so we have a local maximum. And then if we are having a neighborhood such that the point that is there, all the points close to it are above it, then we say we have a local minimum. So those are the things that we talked about, and the Fermat's theorem was actually giving us clarity that first of all, local maximum or local minimum must exist, and then once they exist and we know that the derivative exists on some point C, whereby this local maximum and local minimum are happening, then therefore the derivative must be equal to 0. And that was not meaning that if the derivative is equal to 0, then we must be having a local minimum or local maximum. That is not what it's just the other way around the Fermat's theorem. Today I want us to talk about the mean value theorem. Basically, the mean value theorem is very useful for proving some of the basic results in calculus, such as proving if a function is increasing on an interval. Let's say we have an interval x1 and x2. Then let's say we have a function and it is increasing on this interval x1 and x2. Then the mean value theorem can actually help us to prove that if that function is increasing, then x1 must be less than f of x2, or if the function is decreasing, then f of x1 is actually bigger than f of x2. So we can usually use the mean value theorem. Of course, we're not gonna prove much of these things because within our syllabus we are only focusing more on just the understanding of these things and actually the use of these things. So what is the mean value theorem is saying? Is saying if you have a function, let's say if f is a differentiable, if f is a differentiable function, right, and it is differentiable on an interval. So it is differentiable on an interval. Let's call the interval a and b, right? On the interval, and this interval is actually closed. Then there exists a real number c between a and b, such that this is c, is not e, this is c, such that if I take the first derivative of this function and then I plug in c in it, I will get f of b minus f of a all over b minus a. Equivalently, let me put it like this, or equivalently, we can say that f of b minus f of a is equal to f prime of c times b minus a. So basically here you can see what I was saying, that if you want to prove something, remember that if the function, let's say it is some kind of increasing function, you will actually end up having f of b is equal to f of a plus this whole thing, and this one is not going to be 0 because this is different to that, and also this one is bigger than 1 because it's increasing. And then if this one is actually bigger than 0 and we're having this, then this must be bigger than that. So you can use this one or simply that to prove if a function is increasing, then the output of these endpoints can be actually compared. So another thing that I want you to realize here is that whenever we're talking about the first derivative, we're talking about the slope of the tangent line touching at a particular point. So this one is a slope, and this one is actually the slope of the line passing through this point and that point. If let's say we take this with f of a and this one with f of b, and then we create these 2 points. Let me try and emphasize what I'm saying, because I might be saying something that I think it makes sense, but to someone who is actually studying this, they find out actually that I'm not getting what you are saying. Say, you're wasting my time. So basically, suppose I have a function, and this function can be drawn like this, right? And it is defined there, and at this point here I have a. Of course, the output, if this function here, I'm going to call this function f, and at this point this one is going to be the output of that, or it's going to be f of a. And then if you look into this point here, we're actually having f of b, if this point here is actually our b. So what is the mean value theorem is saying is that if I were to draw a line that is passing from this point to that point, right? Take note that actually here I'm having the x value is a, here the x value is a and the y value is f of a. And then if you look into this point, the x value is b and the y value is f of b. So what is this thing saying? Is saying that if I were to find the slope of this line here, the slope of this line will be y2 minus y1 divided by x2 minus x2. And of course my y2 is going to be this here, which is f of b, and then minus f of a, because this is the y1, and then you divide by x2 is going to be what is inside here, which is just b, and then this one here is going to be a. If I call, let's say, this line is going to be my line G. So m of G is going to be this whole thing here. Now, what is actually this mean value theorem is actually saying? Is saying that there must be a point. So if I were to go here, there must be a point somewhere between A and B, such that if I pick the output there and then create a tangent line that is actually going to pass through this point. Let me make sure that I write something here. So I create a line here. Why my lines are bad? I create a line there that is passing through like this. So I have this line here that is actually touching that curve at that point. The mean value theorem is saying that you can always find that point, and it's going to be the output of some point C here, such that when you are finding the slope of that tangent line, remember that the slope of that tangent line here, this is actually f of c. So the output here is going to be f of c, or that coordinate is going to be c into f of c. So what this thing is saying that if, let's say, I were to, this is going to be t, if I were to look at the slope of that tangent line, remember that if I want to find the slope of this tangent line, I just need to find the first derivative of this function, which is going to be f prime of, and then I plug in this value here, is going to be f prime of c. So what is this mean value theorem is actually saying is that this line here is going to be parallel to that, and if two lines are actually parallel, they are actually going to end up having the same slope. Let me repeat what I said. The mean value theorem is saying that if you have a function and we have the interval, the starting point and the end point. Once you join these two with a straight line, you can always find a point somewhere on the curve such that when you are placing a tangent line, that tangent line is going to be parallel to that. In other words, the slope of this line and the slope of that line are going to be the same. Hence, we are saying the mean value theorem is saying f prime of some value c must be equal to f of b minus f of a all over b minus a. That is what the mean value theorem is actually saying. So you are having this nice thing here. Another example will be, if let's say I am allowed to draw once more, I have a function that is actually growing nicely like this, and then start decreasing, and then start growing again. So you have a nice curve there. And then this point here is not going forever. You have some point there and the function is defined. You have some point there. So this one is actually having an a here, and this one actually is actually saying we have a b. So if you can join this point with that point and then create a slope of these points, you are always going to end up getting f of b minus f of a divided by b minus a. So it's going to be the slope of this line. So what is the mean value theorem is saying? It's saying that you can actually find a point somewhere such that when you're placing a tangent line there, this tangent line is going to be parallel with that, and actually its slope is going to be f prime of, if this point here, I'm going to call this point C1, f prime of C1 is actually equal to that. And also you can also find another point somewhere there such that when you're placing a tangent line, this tangent line is parallel to that. In other words, I have f prime of maybe C2 if this point here is the output of C2. So this is going to be f of b minus f of a minus b minus a. So that is actually what the mean value theorem is actually saying. Let's go back to what I was saying here. I said that just a quick example or a quick sketch of what we can actually do with this. So I said that if let's say you are actually having f, a function f is increasing. I know that this function is increasing on this interval here a b, right? The question is saying to you that prove that f of a is bigger than f of b if this function is actually increasing. So what you will actually do here is not that hard, because what you actually need to realize here is this. You just say suppose this function is also increasing. This is just an example, and this function is continuous, right? So I want it to be continuous and I also want it to be increasing. So I want you to prove that this is bigger than that. So what you are actually saying here, you just say let us c be a number between a and b, right? So x is an element of c is an element of that, such that you have f of f prime of c, and this f prime of c is equal to f of b minus f of a, and then you divide this whole thing by b minus an a. So you let your c equal to that, and then you have this. Now that you are actually having this whole thing, remember that this one, I am gonna say it here, by the mean value theorem, there is such a c in the element of A and B such that I'm gonna call this one equation 1, such that equation 1 is valid. So it's either you're gonna say that by the mean value theorem this happens, or you can just place this and then have this later. You will get a mark for mentioning this squeeze theorem, and knowing that it is that, you will get another mark there. And then another thing that you need to do now, because you are actually having this, so you are having f prime of c equal to f of b minus, this is valid, so there's a dot there, minus f of a, and then this whole thing you are actually dividing it by b minus a. So once you're actually having this thing here, this implies that because there is a 1 there, I can just cross multiply. So I'm going to end up having f of b minus f of a, it must be equal to f prime of c, and then inside here I will end up having a b minus an a. So that is basically what is happening there. And then if you look carefully into this, I'm going to take this f of a and take it to the other side. So I'll end up having f of b is equal to f of a plus f prime of c, and then inside I will have b minus an a. Right. So basically here you can start by saying, since f is increasing, right, then f prime of c is always going to be bigger than 0. So it is a positive number. So that is what is happening. If a function is increasing, you know that the first derivative is actually bigger than a 0. So that is what is happening. Since s is increasing, is that. And since b is bigger than a, then f prime of c times b minus a must be bigger than 0, because this part here is bigger than 0, and then this one here is actually bigger than 0 because b is bigger than a. So separating something smaller from the big, you will get something that is bigger than a 0. This simply means that we are actually having f of b equal to bigger than f of a, because this part here is actually bigger than 0. This part here is bigger than 0. So once I remove this whole thing here, I'll be left with that, and we will not end up having equality. So that's how you would end up reasoning about going about the proof. Of course, this is a rough sketch of what we are trying to do here. And then what are the realistic examples that we can actually have, because we are not proving things in this course, we are actually using these theorems. We don't prove them much. So the first thing would be, suppose this one we're saying, suppose we're actually having f of x, and f of x is actually equal to x squared. Now that we're having x squared, and this one is on the interval, the interval now is specific. We have 1 and 3, right? Now, what do you have to do to actually find out if are we actually having, is there, the question will actually be something like this: is there a point, let me try and write this question here, is there a point C on 1, 3 such that the average rate of change of f is, so I'm gonna say this is 2 times 3 is going to be a 6. 6 minus 2 is going to be 4. 4 divided by 2 is 2. So that would be a question. So what you actually do to actually solve this question, this is what you actually do. The first thing that you find out is that you first have to find out you have f prime of x. So first find the derivative. So the first derivative of that is going to be 2x, and then once you have this, now what is the domain of this, which implies that we have the domain of this f prime is just x is an element of real numbers, because this function is defined everywhere. What does this mean? It means that f is differentiable everywhere. So we have f, it is differentiable everywhere. That is the first thing that you need to know. F is differentiable everywhere. And then once you are actually having f is being differentiable everywhere, which comes from that, the next thing that you need to do, you need to actually end up finding the average slope, or the average rate of change. So the average rate of change, or the average slope, I am looking for f of, so I am going to take this point here as my b, or as my x2, this one as an a. So I will have f of b, which is just 3, minus f of a, which is 1, and then I'm going to divide this whole thing by a 3, and then minus a 1 there. And if you look carefully into this, you are actually having, if I take 3 and I plug it in this function here, we will actually end up having what did I do here? That was supposed to be a 9. 9 minus, okay, let me first complete this. So this one is going to be 3 squared minus 1 squared divided by 3 minus 1, 3 minus 1, which is the same as here I'm actually end up having 9 minus 1 all over 2, which is the same as 8 over 2, which is equal to a 4. So I wanted this one to be a 4, right? So I wanted that to be a 4. So this one here will actually end up having a 4, and then the next thing that you actually need to do here, you actually need to find this constant c, such that if I take the first derivative and I plug that c, I get a 4. And now this was my first derivative. So my first derivative is actually going to be 2, and in the value of x, I am plugging in a c. So I want it to be a 4. And then after that, I solve for c. So after solving for c, I will end up having c is equal to 4 over 2, which is the same as a 2. So once I actually end up having this 2 here, what do I do with it? So the next thing that you need to do, you check, right? You check, is this 2 a number that is between 1 and 3? So because this 2 is a number between 2 and 2, you can just say 2 is actually an element in 1 and 3. That is what is important. And then once you are having this, so I have a number that is in between 2, and then at the same time, when I'm taking this number, plugging it, I'm getting a 4, which is that. So you can actually say that the mean value theorem, in this particular case, it is verified. But if, let's say, someone just wanted you to use a mean value theorem, all you could have just done here, you just have to make sure that the function is differentiable, and then secondly, it is once it is differentiable, because that's what we actually say. Where is this mean value theorem here? So if you have a function that is actually differentiable, there you are done. It must exist that we have a value between these 2 points. That's what is important. But in this example here, we have actually just verified it. In other words, if you do not want to go through this this example, you are just going to say that f of f is actually differentiable everywhere, and you are actually done once you actually prove this. And then you can just say, therefore, by the mean value theorem, there exists a number between these two numbers that is actually giving the average rate of change or the average slope equal to 4, and you are done. But I wanted to do it so that we can actually end up understanding what is happening here. Another thing that I wanted to verify, actually I want to say here, is this. When we're talking about the mean value theorem, some people usually say this thing here. Where's this mean value theorem? Is here. They usually say that suppose f is continuous and f is differentiable. Once a function is differentiable, it is continuous. So I don't have to specify continuity, because once I can talk about differentiability, then continuity is satisfied. You remember when we were trying to talk about that and we proved it. So you only talk about differentiability, but if someone is using both continuity and differentiability, is still fine. But just for you to be aware that differentiability is more powerful than continuity. So when the differentiability is there, therefore continuity is there automatically. So that is why for me, in this example, I was saying all you need to do, just check if the function is differentiable. So because this function is differentiable, then you are actually done. And there are some other realistic examples that are not only applicable in theory. Another example would be, imagine if, let's say, you are actually driving from town A to town B, and your average speed, let's say, is actually 60 kilometers per hour. Then at some point, somewhere along the line, your trip, your actual speedometer must have shown exactly 60 kilometers. There is no way that you can jump the speed of your car in your speedometer can jump from let's say 10 kilometers to 20 kilometers. It has to pass through 60 kilometers. While yes, it might end up just moving so fast that you are not actually capturing it up, but it's actually gonna be something that you have actually, it actually happened in that moment. Let me write this. Just want to give you some real life examples of the mean value theorem. So the first one, like I said, imagine driving from point A to point B, or from town A to town B. Your average speed says 60 kilometers per hour. So suppose you have this average speed. So then at some moment in time, in your trip, it must have shown exactly 60 kilometers per hour. So your speed cannot just jump. And then another example will be, so let me use an example, elevator ride example. So suppose, let's say, you take an elevator, right? Take an elevator from first floor, this is not a floor, this is spelling of floor. I think it's supposed to be like this because I used something else. First floor to the 10th floor. To the 10th floor. Right. Your trip takes, let's say it takes 20 seconds. Elevator is just a lift. Think of a lift whereby you're taking a lift from the first floor up to the 10th floor, and it actually takes, let's say, 20 seconds, right? One thing that you need to notice here is that the elevator usually moves continuously. It usually moves continuously and smoothly. There are no sudden jumps, unless actually there are no sudden jumps, unless of course the lift have a problem. It usually moves smoothly. Now the question is saying here, I write it here. So I want you to see how you will actually address this question. If the elevator moves from bottom to top, can we say that at some point the elevator has had exactly the average speed, had an average speed, right? So what is actually important here is that I had an actually the average speed here. How would you end up answering this particular problem? So to answer this, all you need to do here, you would actually say this this nice thing here. You would just say that which is something that I just wrote here. The elevator moves continuously and smoothly. There are no sudden jumps. So you can first say that the elevator moves continuously, right, and smoothly, right? So it moves continuously and smoothly. There are no sudden jumps, right? That's the first thing that you have to talk about. The second thing here is this. If you look into this elevator of ours, what is this? The elevator is moving from the first floor to the to the 10th floor. So basically, if that is actually what is happening here, the average speed here is actually going to be, we are actually going to the 10th floor and we started from the second floor, right? From the first floor, and the time it took us, it was just 20 seconds. Because if you don't want to think like this, when we're in the first floor, before we press the button, then we actually at 0 seconds, right? And then after some time, which is 20 seconds, then we'll be in the 10th floor. So that's how you ended up getting the average speed of 9, because 10 minus 1 is going to be 9 divided by 20 or something of this nature. 9 divided by 20 seconds, which is actually 0.45 floors per second. So that is the average speed. So we are actually saying in this particular case here, by the mean value theorem, there was a moment in time where the lift had a speed of 0.45 floors per second. So that's what you can say here. We need the mean value theorem, we need the average speed, and then after that, can you conclude? That is what is important here. So you will get a mark for actually talking about this elevator is actually moving smoothly and actually is actually not it's not actually jumping up and down, it's just moving smoothly up. And also at the same time, when we are saying that thing, we are assuming that we would actually be getting a function that is smooth and that can be modeled in such a way that would end up having this average speed here. And this one here was a floor and this one was a floor, hence we're having a floor, not meters. And then this one here was in seconds, hence we're dividing by seconds there. So there would be a mark for that, and there would be a mark or two for this part, and then using the mean value theorem, and then after that for your conclusion. So your conclusion would be I answer, because the question was specific. So here we are expecting you to get a yes, so there will also be a mark there. That's how you would actually answer this question. Another question will be like this. So you have a temperature change example. Change example. So if you are actually looking at the temperature change example, suppose this example is actually saying that, suppose this is happening. First, we'll suppose that at 6 a.m., right, the temperature is 10 degrees Celsius, and then at let's say here we have 12 p.m. the temperature is let's say we're having, let's say maybe 22 degrees Celsius, right? And then we say that the temperature changes smoothly, right, and continuously. Right, no sudden jumps. So what is the question? The question is saying this was, this is not a was, that's a was there a time between 6 a.m. and 12 p.m. where the temperature, let's say, was increasing. at exactly 2 degrees Celsius per hour. And then we place a question mark at the end. Was there a moment in time where that was happening? So the first thing that you actually need to do here is this. So first, this is going to be our solution here. So the first thing that you need to do here, just like we did here, where's this? The elevator moves continuously and smoothly. We need something of that kind. Here, they are already telling us the temperature changes smoothly and no continuous jump. So here you will end up having something like this. You're just gonna say the temperature as it is. So you have the temperature changes smoothly, right? So you have the temperature is changing smoothly and continuously. It is moving smoothly and continuously. So that is the first thing that you need to do. There are no sudden jumps, so it is just changing smoothly. So no sudden jumps. So once you are having that, the next thing that you need to do, we will do exactly as we did there. You want to find the average slope. So the second thing is we want to find the average slope. But our average slope here is the average change in temperature. So we want to say average change in temperature. For me, so that you don't make mistakes, just say the average rate of change and not write anything else. Just write average rate of change. And then after you have done that, what are we actually trying to find here? What is the average of what are we actually modeling here? What is the main thing here? Is it time or is it temperature? If it is time, time will be the one that is going in the numerator, but here we wanted to see, was there the temperature increasing or where the temperature was increasing? So we are focusing on temperature here. So we wanted to find T2, or the last temperature, which is actually 22 degrees Celsius, right? Or just 22. And then we're gonna end up subtracting 10 degrees Celsius, or simply 10, and then we divide this whole thing by the time. So the time here was actually 12 here, 12 p.m., right? 12 p.m. is the same as 12 hours, and then subtract the initial time, which was 6 a.m. So that is actually what you actually do here. And 22 minus 10, you actually know that, okay, 22 minus 10 is going to be 12, I think, and then 12 minus 6 is going to be 6, and then of course 12 divided by 6 is going to be 2. What are the units of the numerator? Is actually degrees Celsius, and the units of the denominator, you place this little divide for the denominator, which is going to be hours. So what is important here is this. Can you see that this number here is the same as this number that was given there? So if this number and that number were different, then you are not going to be able to conclude about the information that is given, because this number here needs to match with what is actually given there. So your final answer, because you have this and you have that, the next thing that you must say is this. You can say that yes, there, what are we trying to use here? Because of this smooth here, you want to end up getting a mark. You want to get a mark. For yes, you want to get a mark. What are you using? So you can say yes by the mean value theorem. There would be a mark for that. There must be at least one time or moment between 6 a.m. and 12 p.m. where the temperature or instantaneous temperature, let me just say where the temperature rate of change was exactly at 2 degrees Celsius per hour. So you can just say this, yes, by the mean value theorem, this must have happened because I have this nice average here, which actually corresponding to the question, and this temperature was actually changing smoothly without any problem. So that's actually one of the things that you can actually say when it comes to the mean value theorem. I hope you can actually get to understand what this mean value theorem is all about. It is actually all about can you actually find, if I give you a function and I'm giving you the interval here, can you actually find a value in between this such that if I take that value and I plug it in the derivative of this function, I get the gradient or the slope of the line passing through these 2 points. We have A and f of A, and then we have B and f of B. So that is what is important here. If I take this point, this A is here, and then this B is this one. So if I take these 2 points, I find the gradient. Can I find some constant, or can I solve for x such that the value that I get is actually in between these points, and the gradient, the first derivative is equal to that value? That is actually what is important here, because in this example that I gave you here, when I was trying to be realistic here, so what was important is that you wanted to find out 1, and then I take this one, I plug it there. 1 squared is going to be 1, and then the another point is going to be 3, and then when I'm plugging it here, I get a 9. So once I'm actually dealing with this thing here, I can find the gradient of the line that is passing through these points as 9 minus this point, which is 1, divided by 3 minus this point, which is 1. So I will end up having 8 over 2, because this is 2, which is the same as 4. So the question was simply saying, can you find some point C such that when I'm taking the derivative of this, which is actually 2x, can I find the value x such that this is going to be equal to a 4? And then when you're solving that x, you get a 4 over 2, and this is just a 2. And this 2 here is actually a value that is between 1 and 3. So that was actually the question. Can you find that value? All this thing that I'm trying to do here is actually the content is actually lying there. So we're gonna stop there, and then we'll talk about later the increasing and decreasing function. To be specific, I want to talk about the interval whereby the function is decreasing, interval where the function is decreasing and increasing, and then after that we actually talk about concavity, and then we talk about second derivative test. Of course, at this stage we are talking about theory most of the time, and then we'll look at the examples once we are actually done with this theory here. Some of the examples that usually come up in the tests and actually the exam. So that's what we will look at after I have talked about increasing function. Let's say we're talking about a function that is increasing a certain interval. or concave down or concave up. So let's focus on that, and then later we'll look at more examples and questions that are more examinable, because this one is just the content and some of the things don't usually come up. They usually come up in terms of multiple choice. So that is what is important.